Welcome to this seminar at the Institute of Advanced Research of Artificial Intelligence in Vienna. I'm David Kreil, and I have the honor of being your host today. Today's speaker is Professor Jiawei of the University of Illinois. He holds the Michael Aiken Chair and is a renowned member of prestigious learned societies such as the IEEE and the ACM. He's the author of a multitude of groundbreaking papers that have influenced the work and has been cited by way over 100,000 other researchers. Moreover, he has shaped the careers of students worldwide with his well-known books and lectures. He can proudly see his own students called to professorships in leading institutions everywhere, from the UC San Diego, Santa Barbara, UC Riverside, by his own University of Illinois to Georgia Tech. His research in data mining and pattern discovery, network analysis, and particularly the modeling, analysis, and extraction of knowledge from textual data has received the highest awards from academic societies all over the world. He's the recipient of multiple awards by the IEEE, including the highest honor that it awards, the McDowell Award and the Japan's Funai Achievement Award. Despite of all these achievements, he has remained a true gentleman, scientist and teacher, a model for us all. Today, he will share his insights on mining latent entity structures, and it's thus with great delight that I welcome Jiawei as distinguished speaker to the seminar.
Thanks to David and to the whole institute for the nice introduction and kind invitation. So for me, I have been to Vienna, to Austria quite a few times, but this time due to pandemic, I cannot come, to give a lecture right on site. So I just stay in my home office. But the background actually is the University of Illinois campus. If we can see, that's the UIUC campus. It's very beautiful. And also now it's almost summer. We just finished the spring semester. That's almost exactly what it looks like if you really go to the campus today. Okay, so let's start. So my talk today is about embedding and the language modeling for effective text mining. As David introduced, I've been working on data mining for many years. For data mining, text mining is just part of it. However, text mining has some specific importance. If you look at any statistics, people will say now we are in a very big data, age. We get billions or trillions. People are counting data now is in the petabytes or even more. However, if you really check the big data, the majority of the big data, like somebody say 80%, somebody say even more, actually majority part are in the form of unstructured data, unstructured text data especially. Of course, you can say videos, audios, images are also, unstructured data. However, to really understand it, like videos, images, or pictures, the majority of people are actually doing some mining, turn them into some kind of a text data as well. So that's the reason why, if we work on big data, we need to do text mining because, natural language text or social media is a majority part or the most challenging part of data mining. Okay, so for this, we actually have the 3 key points to see how we can do data mining on text data. One part, we call this one is embedding. The embedding, that means if we want to get a very high dimensional text data, to understand it, we want to embed them in some lower dimension space. So we can study their similarities, clusters, classifications. That's why embedding is very important. Then the second thing is structuring. That means if we think the unstructured text data, we can get some form of structures. That means we can introduce phrases, types, interconnected entities, relationships, networks, and we also can model them in taxonomy. That will make our data mining, much more effective. So that's the general road network, okay? So if you look at this roadmap, the general philosophy is this, okay? We start from very large corpus. Of course, lots of people may say, we hire some annotators, crowd of annotators, try to do annotation, but that's still very costly because the text corpus keep changing and they are in multiple different domains. Okay. So our philosophy is, instead of getting human annotation, we are thinking about, we have lots of knowledge base like Wikipedia, domain dictionaries. If we take text corpus plus the general knowledge base, then we develop methods to mine keywords, phrases, typed entities, relations, and study their similarities, constructing the multifaceted taxonomy, and also constructing multi-dimensional like text cube or something. Using these structures, we should be able to get knowledge out of it. So that's a general philosophy. Now let's see how we should do it. In this talk, I'm going to give you, you probably see a few acronyms or a few names. These are actually the new research articles. We develop a few methods. We just take those methods just using some acronym. So then finally we can refer them nicely and the people can refer them nicely as well. So I'm going to discuss a few topics right on this. So the first one is how we can understand semantics. We actually discussed text embedding, especially we recently developed a method called jointly spherical text embedding. I'll start from there, then I'll go down to many other methods we use this methodology. So I assume everybody now knows text embedding, especially in 2013, Google actually pushed out a very popular method called word2vec. The general philosophy of word2vec is words are in a very high dimensionality. If you think every word is like independent, like a dimension space sitting there, if you get 10,000 words, you're thinking about you really have around 10,000 dimensions. Okay? That's too much to do analysis. We know the curse of high dimensionality. So the word2vec philosophy is you based on surrounding of the words in sentences, you change this words, very high dimension space, into vector of much lower, like 1 to 200 dimensions. So word2vec general philosophy is mapping, or we say embedding, the high dimension words into low dimension. Not too low, you just say 100, 200 dimensions. However, by doing this, you should be able to see the words with a similar semantic meaning, they cluster together. You can use some kind of a clustering algorithm or study their similarity. And to the extreme, in the word2vec paper, they actually show if you get like a very large corpus, you finally see the embedding space of man and a woman. Then you draw an arrow from the embedding space of the man to women. Then if you find a king, likely you draw a parallelogram, you will be able to find where the queen is. Okay, so that's actually pretty amazing. And people can do even some kind of algebra. After word2vec, actually Stanford developed one called GloVec. It's a global vectorization, you can think in this way. And Facebook get one called fast text. So the methodology, of course, they use different maths. The general philosophy is we map the high dimension words into the lower dimension space vectors, but we map them all in the Euclidean space. Euclidean space, you can use matrix computation because Euclidean space is easy to write in a matrix form. However, if you really look at how you really do computation, for example, you want to compute, you say France and Italy, they have some kind of similarity. If you map France in some dimension space, you map Italy somewhere, you actually will see they are very similar in the sense their cosine similarity, this theta, should be closer to 0. That means if very small theta means if they have very high similarity. However, if you map a bar and a crocodile, okay, suppose they have nothing to do with each other, then this theta is almost 90 degrees, or you say their cosine similarity is approximate to 0. Then if you want to do mass, you say France minus Paris. However, you do not say Italy minus Rome, you just reverse it. You get Rome minus Italy. This computation, almost their cosine similarity is -1, or you say their theta, is almost closer to 180 degrees. And we know that. So what's wrong with it? But you can see is this. When we do the real computation, we use cosine similarity. Cosine, if you know even high school math, we know if you do cosine, you can map them into a spherical space, right? But we compute everything in Euclidean space. So there's a mismatch because when you use it, you actually calculate those similarity in spherical space. But when you do transformation mapping, you do everything in Euclidean space. We know, even you study geometry, these two are different, right? Another thing, you probably also see the word-to-vec may need some kind of improvement. Word-to-vec basically say, if you want to understand the meaning, like harmful, okay, what do? Well, you say, look at plus minus a small number, say 5, okay. However, if you look at this harmful, you plus or minus 5, you cannot find any meaning which is closer to harmful. That means this plus or minus 5, try to find similar words, may not be always beneficial. However, if you enlarge your scope, you look at harmful, you look at here, those bolded words like, alarm, taunting, shot, danger, rock. These words actually somehow quite close to harmful. That means our window should not be too small, like just plus or minus 5. What we may think is, what about we think of multiple sentences or a short document? If we embed this one in a short document, likely even this alarm and danger is pretty far. We still will be able to figure out what is harmful, okay? So this idea basically is we need to think about not just a local context, we also need to think about a global context in the scope of short documents. That means mathematically, you are going to think about, if you want to see the meaning of this central word U, not only you want to see the surrounding words V, but also you want to see the short document or paragraph D. That means you need to think about both, okay? So if we do this, you probably can see you will be able to capture two things. One thing is you think everything you map into spherical space. The second thing is you are not just looking for local, but you're also looking for global context. Then we can do better, okay? With this philosophy, we developed in 2019 in Europe's conference, we developed one new algorithm called jointly spherical embedding. Okay, then we just simplified it into Jiawei. Okay, now, for Jiawei, you probably can see we compare with word-to-vec, Glove, FastText, and BERT, and also compare with Poincaré, Glove. Okay, Poincaré embedding essentially is thinking everything is in the hierarchical way. Okay, then these are pretty large sample data sets. We look at similarity. You probably can see the Jiawei, the similarity actually is higher than many of the previous algorithms for all the 3 data sets. Okay. Now, if not only this, there are several other obvious advantages. One advantage is its calculation actually is pretty efficient, because if you look at your computation, essentially you look at a global similarity, which is just like a conditional under the whole document. Then you look at local similarity, which is just plus minus k. So the computational complexity is very close to word-to-vec. Okay. Comparing to, for example, BERT or concurrent embedding is much more efficient. However, it's quite sensitive. We just show you some example. For example, you study acronyms. You get a few university names like CMU, UIUC, UNC, or Johns Hopkins, JHU. Okay. If you just calculate the local similarity, we actually set up lambda into infinity is global, equal to 0 is local. You'll probably see if you just look at local plus minus 5, the CMU plus minus 5, you will not find anything closer. However, you look at the global similarity, you will be able to find the Carnegie Mellon, Pittsburgh, Pennsylvania. Okay. And UIC, you will find Urbana, Illinois University or something. So you can see, you can disclose something quite nice just because of global context. Another thing for the benefit for global context is you look at a good versus bad. If you just thinking about local similarity, good and bad are usually surrounding words. If you just look at plus minus 5, they do not have too much difference. For example, you say, I bought this product. The quality of this product is pretty good. Okay. But the other guy may say, I bought this product, the quality of the product like is very bad. Okay. You pretty see pretty good and very bad. Actually, to some extent, their context could be very close. However, if you look at a global, you look at a longer text, you find they are very different. That's why their similarity actually is much less similar. Right? You probably can see the global one has some advantage. With this philosophy, we go further. We say, what about we want to take a document, we want to map the words in the document in some kind of space. Not only we can find the similarity, but we also want to have the human input into, some computation. Just think about it like we just say king and queen, okay? No matter in what context you map down, independent of your document, king and queen, where space is fixed. However, you think about this, okay? Suppose I give you 6 names, okay? Richard Feynman, Isaac Newton, Theresa May, Donald Trump, okay? If you say, now my focus is on the topics like politics versus science versus literature. What do you want to do? You actually want the Richard Feynman, Isaac Newton to be closer because they both were scientists. Theresa May and Donald Trump could be closer because they both were politicians, okay? However, if you say, no, I'm more interested in distinguish British versus United States, then what you likely will say Theresa May, William Shakespeare, and Isaac Newton should be closer because they are from England, okay? So you probably can see you want some category names or your focus to impact your embedding. So even for the same names, you want their embedding space somehow different to capture the subtlety. Can we do that? Okay. The current, of course, word to back, even Jose cannot do it. Okay. But we were thinking we need some kind of guidance. When we compute it, we will be able to do something really good to our advantage. Can we do that? Okay. So we develop one we call weakly supervised, or you say category name guided text embedding. Okay. Acronym is called CATE. Okay. CATE means category name guided text embedding. What's the magic of a category name? For example, you say category could be politics versus science versus literature. That's category name. It's very high level. However, you probably can see this category name, if you're really thinking about a conditional probability you want to compute. You give me a document, I give you a category name I want to compute. What you want to map could be this. Okay. You can see the last part actually is a plus minus k. That's exactly like a word to that. Okay. The center part actually is more like a topic modeling. You can see you give me a document, I try to compute the probability of this words in, okay? But the first one is more like you give me a category, I want to get a distribution of this document, okay? So now you see category, document, and surrounding words all will have some impact in this computation, okay? If we think about this, now we really have a category named a guide, both on the documents and on the surrounding words, okay? If we do this computation, we actually put this one into something like a expectation maximization. We call E is expectation or embedding. The R is kind of representative word computation. You can think it's one is expectation, one is maximization. You use this EM algorithm to compute them iteratively. Actually, you will find, of course, this one is in the spherical space. What you can find is you give me center is food. Actually, the surrounding one could be seafood, a steak, a dessert, or salad. But if you give me one is a seafood, the surrounding words could be prawn, oyster, crab, and fish. That computation, actually, that means your category name really played the role. Center around it, you try to compute something very similar, right? So we tried this. Then we found this one is very good. For example, we want to do topic modeling. In the past, the topic modeling is purely on the generative model, okay? That's a latent deletion allocation. I think a lot of people are studying topic modeling. You probably know RDA, you know, even you want to put seed, you get a seeded RDA, okay? However, our seed is in the category name form, but we calculate embedding. That means we not only thinking about it within the document distribution, but also we think about the context, the local one, okay, plus minus K. So you probably can see both from the topic coherence point of view or from the mean accuracy point of view, we are much higher than the rivals. They're all doing some kind of topic modeling. We use large document, New York Times. This is on the location, this is on the topic. Like Europe, we work on look at a food as a center for the category names or sentiment as a category name. You can see we got a very high one. Let's look at the concrete example for you will be convinced. We still take this for topics. Like New York Times, we give the category name. One is Britain, one is Canada. You can see what RDA, seeded RDA, you know, TWE, what they got. And the last row actually is what we got. If you see, look at Canada, you will find the surrounding one is Ontario, Toronto, Quebec, Montreal, Ottawa. These are all the provinces or cities in Canada. You look at Britain, you will find England, London, Britain, Scottish, Great Britain. Okay. If you look at food, you look at dessert, you actually get a pastries, cheesecake, scones, ice cream. You get a burger, you actually can get a cheeseburger, hamburger, Burger King, smashburger. Okay. Even look at a good versus bad. That's the only, you know, supervision we give. You actually can see we got like a bad, we got sickening, nasty, dreadful, freaky, cheapskates. So you probably can see these are pretty interesting. You dig up something really for good sentiment analysis. Not only we can do it for one level, we actually can do it in a hierarchical way. So we developed one called hierarchical topic mining using joint spherical embedding and the text tree embedding, okay? So you probably can see, if you give an article like sports, arts, science, underneath you give something like a baseball, soccer, tennis, like dance, music, film, you give these two-level structures. Then we go down to Wikipedia, we go down to New York Times. You probably can see what we got. The blue one are the given ones. Then the white ones are we dig out from the text. You probably can see, like under arts, we get theater, artist, contemporary, classics, studio. But underneath, you get theater, you get a playhouse, Schubert, Broadway, MacArthur, and Lauter. Okay, so you probably can see it's pretty interesting. Actually, we did some comparison with quite a few methods if we want to do classification. But the interesting thing is, when we did this, that was the starting of the COVID time. Okay, we went to PubMed, the medical research publications. We give a tree, like this part of the tree is biological active substance. Then we give the tree underneath, we give hormone, enzyme, vitamin, and vaccines. So you probably can see the vitamin, you get like vitamins, niacin, micronutrients, carotene. If you know what is vitamin, they give very good ones. Of course, for vaccine, that time there were no like Pfizer or Moderna or like other things. So you won't get that, but you get something which is somewhat closer to vaccine. This is automatic without anybody's knowledge, right? You just based on the correlation in the text, okay, in the words. Okay, so that's about Kate and Josh. Now we get into what about we really want to study the taxonomy. The taxonomy that you give, whether we can derive it. Okay. So in 2017, in ECMN or PKDD, we got a paper called Set Expand. The general philosophy is this. Okay. People give you a set. Barely people want to give you the whole set. They give you a few seats. Like, for example, in US, in the New York Times, you can give Georgia, Illinois, Virginia, you can give 3 seats. Our goal is, with massive text, whether we can generate all the US states, okay? How we can do that without anybody trained, okay? To do this, you also look at the surrounding. This is like a word of back, you think in that way. As you look at surrounding, we call these surroundings skip grams, okay? Using the skip gram, you can derive something. However, you do not know which skip gram is most essential. Okay? Sometimes you can make mistakes. How we can generate some good ones without anybody give us supervision. Okay. So what we did with this. Okay. The first is we try to get some good skip grams. Then we take this skip gram, there are lots of them. We partition them into several, like you can really say, you can sample them into several, you can say groups or clusters. And take each group, you can do some prediction, okay? However, what you can see is for any group, when you do it, you may generate some noise. For example, like this one, you generate something, you may generate, besides you generate California, Arizona, you may generate Quebec, which is a province in Canada, okay? And you may get here, you may generate Baja California, which actually is a province in Mexico, okay? That means they do share some text similarity, but they are not the right US states. But how do we know it, okay? Without anybody's supervision, what we did is we developed one called rank ensemble. That means you, based on these skip grams, the set of skip grams, you can do some kind of ranking. Say which one you are most confident, you put it high, okay? However, the one group to rank them doesn't really count, okay? You get multiple groups. What you want to see is those seeds, they constantly rank high. For example, suppose you look at California, Arizona, and Florida, they constantly rank high. You can say, now I probably will be confident If they constantly rank high, they are all in the high ranking, I pick them up as consolidated one. Of course, for example, you may generate one called Wisconsin. They rank high, but not consistently rank high. What do? Okay, you leave it to the future round. That means you first pick up the very top ones. Then you absorb these top ones into your enlarged seed set. That means at each iteration, originally you probably only have 3. Now you add another 3. Now you have 6 seeds, but those seeds are reasonably good seeds. Then you take those, you run through this whole process again, okay? And you do this after certain iterations. What you got are really good ones. That's the one we first developed this algorithm called set expand. That means if we want to develop the whole set, we do this kind of expansion. Okay. However, this expansion doesn't mean everything you generated actually is clean. We did this, we found that you generate a really good one, but you still generate something a little noisy. Okay, what do we should do? We found where's the noise you come. Actually, when we generate, we start from Illinois, Georgia, Virginia, we try to generate. We may generate based on skip gram. We may generate something like Chicago or Atlanta, which actually is not really the state, but the city, okay? You may even generate like US or Canada, okay? But however, once you generate them, you mark based on your ranking and somewhere you mark them, say these are wrong ones, okay? What do? Of course, people may say, throw it away, okay? Actually, we did not throw it away. What we did was we take this, we already know they are negative. Now we take those -1, we call these as a contrasting set. We let all these 3 sets go in parallel. Okay, that means we try to generate US states with these 3 seeds, but we also have wrong seeds, which are cities or which are countries. But don't worry about it. You generate 3 in parallel. Why you generate 3 in parallel? Just because those things most close to the city, they grab the most closer cities down there. You enlarge your negative sets. States, you enlarge your positive sets. Countries, if you think they are negative, you also enlarge their negative sets. In that sense, what you derive become more stable. Okay. So this one we call set co-expand. That means collaboratively, expand them in parallel. Okay. Another way we tried this. Okay. Not only you can use a co-expand, you can use, BERT or those, language, we call pre-trained language models, because they are trained in a very large text. So what we did was this. Okay, you can see, you may have things like US states, such as Illinois, Georgia, Virginia, you may have such things. What you did is you try to think this one likely could be a name. It could be something like states or US states or large states, but you actually mask them. You try to see what could be the name here. Okay, that means you just think about this one like a class name. Okay, then these are the instance name. Okay, you try to find a class name. Okay, then you use this class name. Try to, the class name, some could be right, some could be wrong. Like, of course, it may not be completely wrong, but it's you want US states, but you may get states, US states or large states. Okay, these are the candidates. Then you go back and forth. For example, you can see Virginia or something like other states. When you can mask this one. However, you can see you mask back and forth, you consolidate both. Okay. Using this way, you can generate really good quality results. Okay. So you probably can see what we can show you a few things. we take US a few laws like Patriotic Act. This one is coming right after September 11th. So Obamacare, you probably heard of this. Clery Act. We take these several laws. We go down into large corpus. We actually got lots of laws, US laws, right out. Okay. We take a few TV channels like ESPN, CBS, Spike TV. We take this as a seeds. When we expand it, we get lots of like CNN, Fox, BBC, those news channels, TV channels. We get wars like World War I, Cold War. Then we put in the New York Times or Wikipedia in those large corpus. We get lots of other wars, if you can see. So that means actually it's pretty effective. You can dig up new things. Okay. We also show, this actually can generate a pretty high quality. If you think about it, in the top 20 we generated or top 50 we generated, actually it's all in a pretty high results. Of course, you may challenge us. You say, oh, what about I set a seed as 50. I say, I get a Canadian provinces. Canadian province getting all together is only 14 or 13. So how could you get all of them? Of course, you force them to generate your in the later part, you may get into cities to be provinces. Okay, but that's a one, of course, it's not absolute right, but the chance to get it expanded without supervision, actually you can get a very high results. Okay. Then what about hierarchies? Okay. Suppose I give you a seed like this. Okay, like a root, I give you US and China, and I give you under US, I give you California, Illinois, Texas, Arizona. What I want to go through the large corpus. You expand at the country level and also expand at the down part, like state or province level. Okay, can we do this? This is a goal. Okay, we want to get it, from US, China, we want to get it Canada, Mexico, and many other countries, and we want to get their provinces or states. Okay, so the interesting thing is we can use set expand, that idea, to generate countries. Okay. But how can we generate down part? That means, suppose we can use set expand, we can generate California, Illinois, get Texas, Arizona. But how can we get a Canada? We can go down. There's no example. We can automatically get an Ontario and Quebec. Okay. Actually, that's a pretty interesting thing. Is we go back to embedding again. Okay, you think about this. Like we said, a king and a queen and a man, a woman, you can do parallelogram. Actually, we tried this. It works nicely. That means you take United States and California. Okay. Then you take China, you do the mapping, something closer to China, you map them. You actually find a parallelogram in the sense, if United States, you go down to states, California. In China, you try to find a parallelogram, you will find like a Guangdong or Sichuan or something. It's a province under China. Okay. In that way, we actually will be able to generate down part. So we use a mutual consolidator. Of course, sometimes when you generate this, you may generate something a little ambiguous. Like under Mexico, you may generate Texas. However, once you find a conflicting one, you can wake up the conflicting resolution to see which one's closer. Then you can get rid of those, likely wrong seeds. Okay. So that's what we got. You can see under like a machine learning data mining, this is the training data, the example. Okay. Then you press C under natural language processing, originally get name entity recognition, information extraction. Now you press C, we can get lots of new ones just to dig through the DBRP data. So if we can see from the like archive and DBRP, we can get lots of very interesting things done. Okay. Of course, you may say, can you guarantee what you generate up and down are good? Is there any way you can control the quality? Actually, in last year KDD conference, we developed a method called seed-guided taxonomy construction called co-rel. It's like a correlation based on the relation extraction. What we did, the general philosophy is this, okay? You can use embedding, you can generate down power, you can generate seeds, but the nice thing is you will generate on both ends. That means you generate from like a dessert and seafood, you want to generate it more. How could you generate more? You're still thinking you are on the right track. What we did was you not only look at their children, but you generate a lot of pseudo parents. So-called pseudo parents is originally think that's a root, but you may find the heterogeneous one like lunch or food or dish, they may contain, like dessert or food or like a food. Under food, you may have dessert and seafood. Under dish, you may also have this. So we try to generate those parents, and common parents, common children can, at both ends, can consolidate what you are going to expand. Okay, that means you use hierarchy, you help your expansion as well. Okay, so this is about a hierarchy. And we did this reasonably successfully. However, one of my PhD students, Jiaming Shen, went down to Microsoft. Okay, Microsoft, they have a academic, like a big scholar program. Okay, they have lots of data, not only in computer science, but also in physics, in other sciences. They got a big tree. Okay, we say we can automatically generate it. They say, no, we don't need you automatically generate because we already have a human got a really gigantic tree. But what they really need is this. Every year, there are so many new papers, new terms coming out. But of course, you can use domain experts, but domain expert is costly and their domain knowledge could be faded as well because there are so many new terms coming out. How could we do it automatically? Give me a large taxonomy, existing one. Can we just based on this? Now I give you the new terms, okay, in the new documents. Can you put them in the right tree, at the right leaf, in the right place? Can we do that? Of course, you want somebody to give you supervision, but remember the tree is really big. Okay, computer science, you get millions of papers almost. How can we do this automatically? Okay, the problem actually seems very tricky. However, if you look at the existing tree, what you can see is these trees give you lots of supervision already. For example, you see machine learning is under computer science, semi-supervised learning is under machine learning, or label propagation is under, say, semi-supervised learning. If you know this, okay, that means you actually give a lot of parent-child children pairs, okay? Those pairs actually is implicitly in your taxonomy. Okay? That's a supervision, okay? Then with this supervision, what you see is you take one, say, hospital room, okay? You may find within the context, you may find the whole thing, what is up, hospital room is under hospital. And then going down, you may have intensive care unit, you have a low dependency unit, you have lots of things. You can see what you need to find is the center one together with their parents and children. Okay, that one, if we know this, we call ego networks. That will help us to judge whether you give a query. We try to find out what is the closest one, whether it's closest to hospital room. We look at up and down. We will be able to locate where this new term should be inserted. Okay. So that's the general philosophy. The philosophy is we take your query concept, okay, Then we know the part of the tree, okay? Then we take a query concept and anchor concept, we try to find the closest one, we try to find their matching. Then based on embedding, based on matching, we should be able to locate where it should be, okay? Of course, there are lots of tricks. With the limited time, I will not give you, the details. It's published in last year's W conference. But what we can show you is lots of things we can do it right. Okay. However, there are still some mistakes. Okay. But the mistakes you can see is sometimes even you think it's mistakes, it is pretty reasonable. Okay, just give you simply say is, for example, you get email hacking. Okay, for this email hacking, the true parents is computer security. However, this is just to show the error analysis. That means that something we did was not very right. Our automatically figure out should be under internet privacy and hacker. Okay, of course it's wrong, but it's not dramatically wrong, because under hacker you may get email hacking, right? Of course, internet privacy is related to email hacking as well, but they would the expert will say this is under computer security. Okay, like a social graph, we actually get a World Wide Web, you get a social network, which is better. So there are something we did not as good, but you actually can see the majority thing we did actually is pretty high. But the thing we tried this, and Microsoft did some kind of like a measure. So if human did our work, we did it less than 30 seconds. You ask domain expert to do it, it will take over 21 days. So what they say is valuable is we can do the first pass, then ask human experts to correct some mistakes. So that will increase the productivity. That means you use our algorithm embedding using this hierarchy to guide it, you get lots of benefit. So we checked, like F1, our overall F1 actually is higher than most of the existing work, is around 0.7. It doesn't mean we can do everything right, but you probably can see the precision may still need to be discussed, but the recall is very high. Simply says we grab everyone, we can put in some place we are reasonably trustable. But of course, sometimes it may make mistakes. Okay. Then we actually can thinking about classification. Okay. With this embedding, with all these, what we want to do, which is typically people may like to see, is you get a large amount of documents. You get so many documents. The problem is people can say for this documents, you can put in the right class. But there are so many documents, a limited human, you put in the right class, you even use human annotation, you have to annotate a really large number of documents. What we are chasing is we call weakly supervised text classification. Weakly supervised means you only give a very small number of label data. How small it is, we get like tens of thousands of documents. But what we need to give the label is you either give like a small number of keywords like politics, sports, technology, or you give for each document, you give a bunch of sample keywords, or you give a few label documents. So this one is about politics, this one is about sports. Okay. So what we develop here is we actually use this embedding. We create, it's more like a pseudo document generator. What is pseudo? Pseudo means we actually, based on the embedding, we kick out some, probabilistic, it's more like a generative probabilistic model. We generate something. Why you want to generate something? Just because the thing you give us actually could be very scattered, very biased. But we have lots of unlabeled data. We work together with unlabeled data. We can generate something which we're reasonably confident in different classes. We take those pseudo documents, we feed them into neural networks like CNN or RNN. And then we can train this neural network to generate good results. That's what we did in 2018 and 2019 on a hierarchical way. But for this talk, I'm not going to give you detail on this papers on the, using the pseudo generation plus neural networks. What we actually found is we actually need not only this, we needed a pre-trained language model working together. I first give you a counterexample if you can see why we need that, okay? For example, I give you 2 sentences you can see is very tricky. This sentence, like I said, the oldest annual US team sports competition that includes professionals not in baseball, football, basketball, or hockey. It's in soccer. You probably know US, actually soccer is not as popular as a US football or baseball or basketball. But that's what they said. Actually, the oldest one is soccer, okay? So this one, the sports is really mean sports because you look at surrounding baseball, football, and soccer, you know this is sports. However, there's another sentence, also use sports. But you look at it, you probably see there's nothing related with sports because they say Samsung's new, this mobile phone sports built in, 1.5 gigabytes hard drive, or something. But you see why they call sports. This sports means it has nice feature, okay? So that's what people like to say, of course, you go down to dictionary, you may find that the English sports may be used in multiple different sense, different ways. But the problem is, if you take sports so seriously, you make mistakes. But how we can correct this? We have to base on the context. That's what pre-trained the language model, because they take care of the context. If you go through BERT, okay, just mask the sports, what you will get? This sports is a real sports, you get it like baseball, handball, soccer, you get all these. But this sports, actually, once you mask it, they will not generate sports. They will have like features, includes, or have, or incorporates, requires, or something. You get this. This actually replace sports probably is more proper. Then you can see you need to integrate the real text together with your keywords. Keywords should not be purely independent. Okay, that means I'll go back to the previous one. That means if you see this, is you need, not only you need the embedding, you also need the context. You need those pre-trained language model. With this pre-trained language model to go through the real text, we give only the neighbor name, like politics, sports, business, technology. You probably see those labor name is you pick up the most important, category name. You try to embed them using embedding, using pre-trained language model. You go through large text. That's what you will get. You probably can see at this point, the sports, you get a game, sporting, game, athletics, national, soccer, baseball. You get all these. These are really, really related to sports. Okay. So with this, the power is now you only just need labor name, what we call category name. That's why we developed a new algorithm in 2020, last year, NRP. We published a paper called lot class. What is lot class? Lot class means labor only or labor name only text classification. That means you don't need to give us anything. What we need is just this labor name. Okay. With this, it's very weak supervision, but we get a very high result. You can see. We call this one as a weakly supervised approach. This is our log class. This Genius, DBpedia, IMDb, Amazon are very large data sets. Okay, they have so many documents. However, you can see we get this precision. This log class, the classification accuracy. Here you can see we can get 0.8 or 0.9. Of course, comparing with fully supervised, like a bird. What is fully supervised means you actually give almost thousands of labor documents. Okay, then you actually try to train it. You can get even better using bird. But if you only give us like a labor name or category name, you still can get a very high accuracy. Then we did this measure. The measure basically shows we have only one label, but our label, you can see this red horizontal one is our classification accuracy. This is the bird. You feed in different real labor, like per class, you give labor documents, how many, okay? We aggregate like a 48. 48 means the cross point is 48, means our one label, category name label using our algorithm, compared with bird, supervised bird, they need 48 supervised documents, labor documents per class. They achieve exactly the same classification accuracy. Of course, if you per class you give more labels, you can do even better. Like per class, you give 100 labels, you actually will beat our algorithm. But that's, in many cases, you really do not have that many labels. You really can just think about it, just give a category name, you can do it. Okay. So this is a log class. Finally, I probably want to show you another algorithm, which is quite interesting. This one is just accepted in NACO this year's North America ACL conference. Okay, but it's a pretty rare task. The task is this. Okay, you get lots of scientific papers or product profiles. You get lots of documents. Okay. And you have so many classes. You think about this. And you give me a document, I want to put in the right class, but not only one class. In many cases, you don't want to just put one class. You probably want to give me a set of relevant classes. That means you give me a scientific paper, I can say this one is deep learning, but you may also say, oh, this one is about a bird. Or this one is about some, sentiment analysis or something. You want to give multiple ones, but there are so many candidate classes. Can we do this? Can we do this almost without supervision? Okay, so that's the trick. So you probably can see, what do we have? Actually, what we have is taxonomy. That means you have to give me a taxonomy. That taxonomy, quite often in computer science, people can provide a taxonomy. Now you give me a document, say where this document should be. Okay, so that's the key. That means you give me a taxonomy, you give me a document, say where this document should be labeled. Not one name, but a class of, a group of names. Okay, so that means this one we call taxo class. That means we use taxonomy to do classification. But it's a multi-label text classification. We do not want you give only one name, but give multiple names. Okay. So what we should do? The philosophy is this. Okay. The first important thing is taxonomy give us actually a lot of information. Okay. Because like we said, taxonomy, you actually know what is underneath, super one, these are the training data to some extent. Another important thing is you give us documents. The documents may contain lots of keywords. And what you can think about is you take this document, you do we call top-down exploration. Top-down means you start from this keywords, you look at the top level to say likely this one where it should be. Then you look at it, for example, like you look at this document and say, oh, this one is more on information retrieval than data mining, not on theory at all. Okay, now you first say, now I go down to information retrieval, to data mining, I go down. Then I'll see whether this one under this level, what is similar? Or you may say, oh, this one's similar to learning to rank, but definitely not query expansion. So you can see those marked nodes are the candidates. But if you use top-down search, you will substantially reduce your search space, right? Because you don't want to think about there are 2,000 classes. Actually, each level, they probably only, you just think about it, suppose this one is 10. This 10 times 10 is 100. The other 10 times another 10, you get 1,000. You may have 1,000, but you get 3 levels. Each level, you just pick up the top 2 candidates, or 1 or 2 or 3. You can go down, you can kick out something, you finally will be able to get it. Okay. So, but how to get it? Okay, we found what important thing is you try to find the core classes. That means this document is most similar to which one. Okay, that means you may say, this one is about information retrieval, you give a confidence. This one is about learning to rank, you give a confidence. Then you find this one is SVM rank, you give a confidence. Then you may find maybe this SVM rank, the confidence the highest. That means you actually find a core. Okay. Then you find their siblings, likely they are not this. You probably can see quite low. What you need to think about is, this one's core. You can go down to its parents or grandparents. You can grab something. Those are also candidate labels. So you probably can see what you need to think about is you take the most relevant core class. Okay. Then you, based on this, you try to, based on their parents or grandparents, those relationships, you do reevaluation. Okay. Then you will be able to find it. Okay. That means we start, identify the core class, then we generalize from the core class with bootstrapping and self-training. Then we can for each one, we will actually try to find its core class and its parents and doing the mapping, doing the self-training. Then we will be able to find very good labels. Okay. So what you probably can see is this. This is DBRP data. This is Amazon data. You probably can see, actually, it's not that easy. You just see, like the Amazon data is most the easiest one you can understand. You say, when our son was about 4 months old, doctor said we could give him crafted cereal. So we bought a digested or something. You probably can see this is the review report. You want to put this document, say where it should be. Okay. Of course, all these, you have hierarchy, you have embedding. You probably can see from here, you may find a core class. Sometimes you may find more than one. Okay, like this one. You may find a crafted cereal and a baby cereal. These two likely are most relevant. Then how you do it? Then you grab other documents. Their parents, especially you can see they have a common grandparent. Okay, that means these likely are good classes you can get. So you probably can see you finally give 2 core classes, you get 3 other labels. They actually could be all good labels. That's what we did to give you multi-class classification. And using this hierarchy, we do not need other supervision. We can get actually very high quality. So this is our newest paper, NACL. Actually, I think NACL just published 2 weeks ago. And this one, you can see Amazon data and the DBpedia data, we all get a pretty high quality. So you probably overall, you can see the embedding, the pre-trained, and the taxonomy. Those are the keys. And you also see the documents we need to label. Actually, it's very small. The reason is we have the taxonomy. And then we actually, comparing to the others, we actually can get It's almost like a bird has to give, per class has to give, like 50 labels, okay? And that's what we can achieve, okay? So finally, I can show you some interesting case studies. We actually got quite a few case studies. One is about Russia, Ukraine, those conflicts. We actually analyze based on a very small number of keywords. This one is about 2019 Hong Kong protests. That's a picture. So, but you can see the label name we give actually is a very small number of labels. Like per class, we put them into 5 classes try to grab the keywords: political, police, economic, information, infrastructure. Some are too abstract, like infrastructure. Barely people actually use it. But we give a few examples. Like infrastructure means like a Hong Kong University, transportation, international airport. We give some hints here. That means these are the meaningful, too abstract names. You actually need to give some examples, but only very small example. Then you go through the large pile of Hong Kong protest data. You probably can see we dig out something pretty interesting. Like a political, you look at these are all political. And you look at the police, these are like a water cannon, pepper spray, petrol bomb, like these are all the police treating the protesters. And that's a media, you probably can see the both sides. Chinese state media, BBC News, Global Times, and Sina Weibo is the China's, that's the Twitter. That's internet censorship. Those keywords, we all grab it. It's pretty much related to the information war. Okay, so that means we really can, without anybody give us a real supervision, we just need a few keywords. Then we can grab the most relevant one. We can do classification. We can do a lot of in-depth study. Okay, so the general philosophy you can see is we go back to this. See, our goal is we take large corpus. We do have some knowledge base like a Wikipedia or dictionary. Then with almost no other human supervision, we can dig through getting taxonomy, getting classification, getting multi-dimensional cubes. We can derive knowledge out of unstructured data. So that's our goal. If you look at our group, actually we go from data mining, that's like a textbook I wrote starting 2000, and we got into link mining, mining heterogeneous information networks, mining latent entity structures. That's like 2012, 2015. Then recent years, you can see we go deeper and deeper into the text. But on the other hand, you also see with this study, actually we got even more recognition because almost every year's SIGKDD dissertation award, we either get an award or get a runner-up. Okay, that means actually the award committee look at the student dissertation. They think they did a really great work, really milestone work. For example, like Xiang Ren now become the professor, assistant professor at University of Southern California. Chao Zhang is in Georgia Tech. Jia Lu is in Google Research. Jin Boshang is a professor at UC San Diego. Okay, so what I actually give you the papers, all the research papers I lectured or referenced here. But the nice thing is, if you look at the first authors, we have 3 stars. Jiaming Shen, actually, he is graduating. He will join Google Research this year. Yu Wang, you get lots of his work. He received this year's 2021 Google PhD fellowship. Google actually for the structured data and database, this domain. Every year in whole North America, they only give 1 award, and he got it. And Jiaxing Huang, she received 2021 Microsoft Research PhD fellowship. Microsoft Research total in whole North America a year, they only give 10. In all the computer science field, they give 10 PhD fellowships. And she is one of the recipients. So that means, you know, our work, not only academically, we can generate some good papers, but it actually is recognized by Google, Microsoft research in substantial way. Okay, so I should put an acknowledgement here because our work actually been supported by lots of funding agencies and industry as well. Thank you. So I'm open for questions.
I guess the first question I actually had, and I think David tried to pose, was could you please elaborate a bit on knowledge discovery from the last slide? In particular, do you have some concrete examples? Did such tools discover some knowledge that humanity was not aware of yet? If not, what would be necessary? And that's a question from Mario.
Oh, I see. Yeah, for the knowledge discovery part, of course, you know, from the text, what you can find, the majority are the things already in the text. Just a human may not be able to dig it out as easily as, you know, like sometimes, just give you an example, okay? For example, the biomedical data. We did one study, which is interesting. That's a story sometimes we use. I can give you the story. The story was this, okay. We, a few years ago, we got a large funding from NIH, which is National Institute of Health, the medical things. We're not doing medical, but they know we are doing data mining, so they give us funding. So I went to UCLA Medical School. Okay, they want me to give a talk, say what we are doing. They are medical scientists, doctors, okay. I give a talk, I show we can find something quite interesting. For example, in the US election, that's 2016, that year Trump actually got it. In the debate, there were lots of issues. We try to summarize the issue, give it a category name. One is like a gun control. One is immigration. One is like a crime, or, you know, you probably know all these in the US commonly discussed. Then we show, for example, under gun control, we show the phrases we dig out. For example, for gun control, you may have gun laws, gun rights, you know, like mass killing or high capacity magazines, all these things. We actually show, we show a list of things. One list is under gun control, we have all the top ranked lists of the phrases. Under immigration, they have the border wars or something, you know, right down there. Of course, that's related to debates. But the UCLA, those professors came back to me and said, this is truly interesting. We really love your gun control example. I just say, probably it's not that useful for you because you are doing medical science. They say, no, it could be very useful. Okay, then they give us a task. What they told us is they are medical doctors, they are cardiologists. They say, actually, you give those different categories like a gun control, immigration, you know, military or something. We have categories as well. Our heart disease, cardiovascular disease, is not one disease. Actually, there are 6 major categories, like a cardiomyopathy, which is a muscle problem. And there are some like a valve problem or synchronization control problem. They actually give us 6 major categories of cardiovascular disease. What they told us is this: nowadays in the modern medical science, you're not treating symptoms, you're treating the root. Where are the roots? Proteins. So they show, you know, they are treating proteins, they actually treating the disease. There must be some protein anomaly. But they said, actually, it's not that easy because everyone give you hundreds of different proteins. You are not sure which one is most important. Okay, Then they say, you got a very smart algorithm because you think about the newspapers, give you all the keywords. Then you can give us gun control like gun laws, gun rights, or high capacity magazines. This actually is a very smart algorithm. They say this smart algorithm, you can do it for us. We say what we can do. Then they say you go to PubMed, you type in cardiovascular disease. You restrict the year to the last 20 years. How many documents you can find? We type in, we find 500,000, more than 500,000. They say that's enough. More than 500,000 articles on cardiovascular disease in the last 20 years. Now we give you 250 proteins. You were thinking about the 6 categories. It's more like immigration, gun control, all these things. But now this category becomes cardiomyopathy, valve problems, heart attack, or like AFib, which is asynchronized, heartbeat or something. Get the 6 categories. You list top 10 proteins, not top 10 keywords, not like a mass shooting or something. You list this top 10, proteins. We list top 10 proteins. After running, we send it to them. They say this is the great results. Why is it great result? We are not medical scientists. Then they say, because you are medical science blind, we trust your result is good. Why? They say you list top 1 protein. All the proteins medical science are used for treating cardiovascular disease in this category. Your number 1 is perfect. It's exactly number 1 we are doing. However, you list top 10, especially top 2, top 3, top 4. Actually, so we spend long time trying to find which one should rank high. We say, why you cannot find it? They say, first thing is everything's mixed up. We have so many things, so 250 proteins are most popular mentioned. They're scattering all those research literature. Another thing is there are so many literature. Many of them are not even medical reports. They are doing experiments on mice, on animals. And another thing you think about is every year there are more than 1 million documents put into PubMed. All those medical doctors, who can read 1 million documents a year? Nobody can do it. Okay, only computer can do it, right? So you dig out this number 2, number 3, number 4. Actually, it's a gold for us because we searched so many years. You think about if we try to do the same thing, everybody will spend 40 years just marking those articles with characters. Okay. You did it in a few hours, okay? So they say, actually, there are number 2, number 3 for 1 disease, which is critically important. Why? Just because they treat the aged people, number 1, it works. They treat newborns, very young children, it did not work at all. But they don't know what other proteins they should dare to treat those young babies. But now you give us number 2, number 3. It's a very good clue. We will start treating young mice. Okay, you probably can see that's what our discovery, but they are so excited. They actually get a monthly, for last several years, get monthly meeting with us, give us tasks for tax mining.
Wow.
So you probably can see it's useful.
That's amazing. I have to say it's fascinating, really fascinating. If I may, I would interject one technical question, and then there is another actually question that goes right at the heart of this, and I'm very interested in. First, maybe the technical one. Can you estimate the likely probability of an error percolating through the iterative set expansion procedure?
Yeah, we actually did it. If you really read the set expand paper, you'll probably see we did have error analysis there. Mm-hmm. We should say that, for example, like for US states, the top 10 or 15 are really, really good. Okay. Then while it's going down and down, you start getting noise. The most dangerous noise is once you get noise, those noise can hijack you. That means if you get, suppose you get a California, then you get Baja California. Baja California actually is a province in Mexico. Once you can get Baja California inside, it becomes a disaster because they grab many Mexican provinces and put in the US, right? So that becomes a disaster. That's exactly, you can see why after SET-expand, we actually got several other articles try to control it. Because you don't control it, you have no training. You're just based on massive data. The top several, we use this rank ensemble. We did it quite well. But once you get down and down, you get into the low part. This long tail become a little messy, but once it become messy, it become even messier. Okay, that's exactly the reason we actually develop like a set co-expand, like CG-expand, you know, like all these things. Even that, if you look at the one we can show you, is if you look at this, we get a originally SET-expand, you get into 50, the F1 becomes 0.7, right? Of course, you get top 20, you get 0.92. But with this more method adding in, we start getting better and better results. It doesn't mean we solve everything, but at least we are confident comparing to many other methods, we actually got better results. It's still not the end of the game, okay? It still cannot be the, you know, the very careful, you know, annotated domain experts, but we are getting closer.
Very nice. I mean, I guess given that we've actually, or you've demonstrated that you can extract knowledge that wasn't there before, where do you think this technology is? I mean, do you think it's at its final stage and this is a general tool to do this? Or are there obstacles you see where this may not be able to scale? Where do you think this is going?
Yeah, we are thinking one important thing is the very basic thing is name entity recognition, information extraction. That part until now, from our point of view, is still a bottleneck. The reason is, okay, you get very large documents. For example, recently we work not only with medical scientists, we work with chemists. If you study, you know, organic chemistry, you pretty know the name of the chemical compound could be very, very long. And some, they even in the middle, they may have other things like parentheses or dash or comma, anything in the middle. But for chemists, they can recognize what it is. Okay, for the people outside of chemistry, they even do not know where to put a boundary of this very long chemistry or articles. That means in reality, there, even just for English, you can see, there are still lots of open problems to solve. It doesn't mean we already solved all the problems. We are still working on, even recently, we work together with the chemistry department, chemical scientists, okay? They give us lots of guidance, say how to do this chemical NER, name entity recognition. So we are still working with them. I should say it's a very interesting domain. The reason is there are more open problems rather than closed one. It means we are not even say we are polishing the wrong ball. The ball is not round at all. Okay.
I like that one. So what would you personally say is the biggest challenge or one of the things that would impress you most? If tomorrow morning a paper were published and said, here you go, here's a solution to X.
Yeah, I think actually recently the language model, the pre-trained language model is very powerful. You probably see people actually spend very many, we call compute. That means a big computation power, digging through the massive amount of, even unlabeled data, is the word knowledge, all the word that ever appear those in the documents or in the social media, they try to build the models. I should say that's one direction we can go, we should go, people are moving in that direction. Another direction actually is develop smart algorithms, like on the information extraction or something. That means feed in human knowledge together with the pre-trained or embedded this model. We can make a good progress. I'm still thinking one important direction we are pushing is self-supervised or weakly supervised. Because you ask human to do labeling, no matter what, it cannot be scalable. Okay.
Yeah.
When we work with the chemistry, those scientists, we deeply believe, because how many types they need? They almost need hundreds of types. You think about it, you say chemical compound, but they go down there, so many down part, different things. Okay, even you give one, say catalyst, you go down there, so many different kinds of catalysts. You still want to label them or get them. You get into stage, human almost ran out of weight. It means you need several hundred types. Even you hire, say, 10 top domain experts in chemistry, they may give you inconsistent labels.
Yeah.
Because you go down so low. That's why human annotation cannot be scalable. You have to rely on the real taxonomy, real domain knowledge. You do good work. So machines still finally can win human. That's why we believe.
I like that a lot. You mentioned unsupervised methods. I think also our last speaker in the seminar series made an interesting observation about OpenAI's CLIP models, for instance. I guess, what these models or other models are trying to do is maybe use different data sources and conflate them, so that somehow what's in the text and what's in the image help each other as a new kind of context. So I was wondering, were you referring to that when you said this is maybe something in the direction you're thinking, or?
This is a good direction for sure, but we are not.
Yeah, sure.
Yeah, we are not so good on the image analysis. I should say we have to work together with lots of other domain experts try to solve the problem, right?
Fantastic. I have quite a few more questions. If you still have a few minutes,
Sure.
I shall try and make them as quick as possible. To what degree can you make your model self-tuning, and to what degree do you need to tweak parameters for the sensitivity and specificity?
Yeah. So for the what I probably should say is a self-training. Usually, if there's reasonably standard way to do it. For example, you are not looking for like psychology or something which is very tricky. If you just a plain like those medical science or chemistry, they are very standard. They use the language, they use something in a reasonably straightforward way. There's not much metaphor, like a deep implication or misinformation, all these things inside. We think we can move on to get good results. We are reasonably confident. But the big open problem is once you stretch the meaning, like you get some implication, metaphor, or misinformation, all these, including psychology, including cultural norm, all those things getting in, things become messier and messier. We actually fear we still stumble in those domains. we probably need, more help from the social scientists, from psychologists. That's a part of the computer scientists that probably have to say, we still have a long way to go. Yeah, nice. If you look at the specificity or, like doing the measure is not a typical measure. You actually have to work with those social scientists, the linguists, like psychologists, those people working together. That's a big domain unknown to us.
Understand. You mentioned your inspiring success in helping medics with your text mining approach. Is vocabulary size an issue there? And I think it says in practice, for example, can you encode names for more than 50,000 human genes in your models?
Yeah, I think we are still working on that. I should say is you probably can see we spend time working on taxonomy. Okay. Mm-hmm. We believe the taxonomy can help us a lot.
Very nice.
Just because the taxonomy itself actually is lots of domain experts or massive text data try to finally say this branch should go this way. Actually, yes. You use a massive, labeled or unlabeled or domain specific or dictionary or Wikipedia. You work on those constructed, very carefully designed multifaceted taxonomy, that will help us. That's why in this talk, you probably see, we spend pretty much time working on the taxonomy. And we use taxonomy to guide us.
Very nice. I have another question. In your medical example, you mentioned the top 2 to top 10 proteins, and the medicine scientists were impressed that you can predict it. But in some way, this is in inverted commas only what is written in the literature. We don't know whether this is truly the top 2, top 3, and so on. Did I understand that correctly? And what if humans see it wrong in the literature so far? Could you see more type of significance?
Yeah, actually, you'll probably see if you read only one article, you really cannot figure out. The reason is you get 500,000 articles. Sometimes something you have a noise cancellation some way. That means you get one article, you cannot really make any good decision. But you get so many articles, you get a correlation. And they do have some noise, but you get a massive documents. Somehow you finally rank with that huge amount of documents. You really have some magic better than a single document can carry. So that's why mining massive data, of course, you still want to get a good documents. That means that's why we get into PubMed, because almost every article, even you get 1 million articles, every article was properly reviewed, right? So it contains something you can trust. So that's why we think actually to get a properly reviewed quality documents, you still need a massive document to get a consensus.
Understood. Another question, actually the last question, sorry, I didn't mention the person who asked it, was Mario Kren. I have a question from Gandia Mobasher, and he says, thanks Professor Han for the great presentation and useful insights. I was wondering if you could give us more detail about the open problems that you have mentioned related to chemical and biomedical texts. Another question, from your point of view, what is the main drawback of BioBird over Josie?
Oh, I see. I think actually these are good questions. The first thing is, I think BioBird or the concrete one we think it's like a bird. They all be useful, especially BioBird is constructed under the in the biodomain using lots of massive biomedical articles. Definitely is very useful. However, all those usefulness, you have to think about this just one tool, okay? What we are thinking is you get your good piles of documents. You need to decide. There are several major things we can do, okay, or we are doing. One is this we call it, taxonomy construction and refinement, because the biomedical doctors or scientists, they give us the high-level taxonomy. You need to use this high-level taxonomy with massive data to enrich this taxonomy. Like you said, suppose you give us genes or like proteins. Even under these, they may further partition and divide it. But once the biomedical researchers, they give you a good high-level taxonomy, the problem becomes you need to dig out massive text data to fill up this taxonomy with the real instances. That's the work you actually can do data mining to do it. That means, like you said, you give me genes, you give me like say 50,000 genes. Okay. Should I output this genes? But some gene name actually is also carries same name as a chemical. Okay. So whether you should put this one under gene or under chemical. Actually, it's a very interesting question. What we did is we first take the whole corpus. We, based on the scientists give us taxonomy, say that's the level of granularity you need. Then what we did is we actually plow through massive documents. We put instance underneath this, if really we can judge it's underneath this. But like if this gene, you have both. You have like occurrences as a gene, occurrence as a chemical. What we need is we put in both, we just put the proportion. Like maybe 80% is gene, 20% is chemical. We put statistic down there. But we don't do the judgment until you give us a real article.
Interesting.
Once you give us a real article, we actually doing sentence classification, document classification. We determine, for example, you give us this name. If the surrounding are genes, you will be pretty sure this one is gene. Or if this whole article is about the chemistry, likely this one is a chemical. So what you do is you do not make the final judgment at the taxonomy construction time. You make the judgment where you get this article, you make the right judgment. So there are lots of tricks, but we think it's very interesting.
Very nice. I have a final question, if you still have a second. So it's from Alexandra Grusha. She says, thank you very much for the extremely interesting presentation. You mentioned that for PubMed, you were building a taxonomy to search for papers. Did you maybe compare it with the mesh terms that are used by the PubMed search engine?
Yeah, we actually take a mesh term as part of an input as well.
Ah, okay.
That means we take a mesh term, we take large corpus, we take, finally we constructed, because you think about the mesh term itself, it was constructed by thousands of medical scientists. And they may or may not even agree with each other. So you do not really treat them like this structure is a god. Okay. We basically, for a certain domain, we ask this domain expert, what's the taxonomy, what's the resolution level they need, they really want. Then we, based on this, we take a mesh term, take Wikipedia, take lots of other things. Then we redo the work for them. That's what our methodology.
Fantastic. Professor Han, I thank you very, very much for an extremely interesting talk. And I'm sure David says hello as well. He's very sorry about the sound problems.
I'm sorry about
there you're back.
David, now we can hear you.
Thank you very much, everyone, for listening. Professor Han, thank you very much again.